Welcome to the third part of Unit 6. In this unit, we're going to explore free body diagrams, which are a way of keeping track of what forces are acting on an object and in which direction they're acting. So to begin with, this is the same slide as from the last part, just reminding you of the labels. So the first subscript is the thing causing the force. The second subscript is the thing experiencing the force. And then capital F for any generic force, N for normal force, F for friction, W for weight, and T for tension. Okay. So what is a free body diagram? Well, you start by representing whatever your object is with typically a circle, though sometimes a square. It doesn't matter what the object is. That circle could be a cow. I don't know. Physicists get made fun of because we turn everything into a sphere. Well, here you go. I made my cow into a sphere. And now I can think about the forces on the cow. I can think about the fact that the cow is standing on the ground. So there's a normal force between the ground and the cow. I can think about, well, that cow has some mass. So there's a weight force between the earth and the cow. And there might be other things acting on the cow. But this is the start of the cow's free body diagram. You represent the object by a circle or square, and then you draw arrows representing the forces in the direction that the force acts. So the next few slides are just thinking about examples of free body diagrams and what they would look like. So the first one, we're going to deal with a nail sitting on a shelf being pulled by a magnet. So we represent the nail by a circle. Earth is pulling down on that nail, so W for weight, Earth for the cause of the force, N for nail in this case is my second subscript. Okay. The shelf is pushing up on the nail, so normal force between the shelf and the nail. So notice we have two different N's floating here, but one is capital, meaning it's one is large, meaning it's the force, the other one's the subscript. Okay. We have the magnet pulling the nail towards it. Now, we don't have a letter for the magnetic force, so this would be a good example of when capital F would be a good idea. So force from the magnet on the nail. And lastly, most shelves that I've seen have some friction between them and whatever's sitting on them. So friction between the shelf and the nail. Now, look at the free body diagram for the nail. Notice that the second subscript for every force on that free body diagram is the subscript for the object which that force is acting on. So in other words, all forces that we're looking at here act on the nail, and nail is the second subscript in every case. That will always be the case with a free body diagram. If you ever have a free body diagram where the second subscript is not the object for which you're drawing the free body diagram, you're doing something wrong. Okay, so let's take another example, which often students want a force on the bottom box that isn't there. Okay, so let's draw the free body diagram for the bottom box. And we have the weight. This is one of those cases where a slightly oblong circle, more oval would be good, because we're going to have multiple forces going downward on this guy. So we have the weight of the earth acting on the bottom block. Okay. We have whatever surface this is pushing up on the bottom block. Now, usually in class, when I ask what other forces are on this block, the answer I get is that there's the weight of the top block. Okay, so now let's think about weight is always caused by another object. On Earth, that other object is always the Earth. If I were to take my two blocks to Mars, the second object would be Mars. Okay, so this would be the weight of the Earth on the top block. Well, that's not right. Because notice this is the free body diagram for the bottom block. So all my second subscript should be B, but that is a T. So that's no good. Let's get rid of that. What is actually happening here? What is actually happening here is the top block is sitting on top of the bottom block. And therefore, the interaction force between them is a normal force caused by the top block on the bottom block. Okay. If, as we will see, I believe in the next part of this unit, if it is the case that this whole thing is not accelerating, so it's in equilibrium, then that normal force between the top block and the bottom block will be equal to the weight of the Earth on the top block. And it will do exactly what you want it to. But if it is accelerating, that's not the case. And again, we will look at that more in the next part, I believe. In preparation for the next part, let's look at one more possibility. And for this one, I want you to have a thought about what I'm thinking about. I have an elevator. I know it looks like a block, but that's okay. Elevators are suspended by cables, so there's a scale. Inside the elevator is a common everyday bathroom scale. Okay, because who doesn't put a common everyday bathroom scale inside an elevator? It seems perfectly normal to me. And then, of course, since everything here is perfectly normal behavior, what do you do if you have a scale in an elevator? Of course, you stand on it while you're riding the elevator. Right? So I want to look at the forces on that scale. Okay, so what forces are there? Well, the elevator is holding it up, so there's a normal force. Normal force from the elevator on the scale. There is the scale's weight, and there's also a normal force, and this is another case where a more oblong would be good, a normal force from the person on the scale. Okay, now remember what I said a minute ago. If this whole thing is not accelerating, then this normal force between the person and the scale will equal the person's weight. But if it is accelerating, that changes. And that is one of the examples we are going to be doing in the next part.